Well, good morning, everybody. Welcome back. Congratulations on surviving a 4-day weekend. Some of you are like, it wasn't a 4-day weekend, Mr. Balogh. I had to work the entire time. It's true. I used to do the same thing. So let's see. The next vacation, I think, is spring break. Right? So we've got a bit of a slog, right, before we get there. I didn't check to see when your next exam is. It's like, is it 2 weeks from this week? Whatever March 5th is. Yes.
That's 2 weeks.
So we have this week and next week for class, and then we have test week, right? We do have lab this Monday. I know it feels like it's been forever since we've had a lab. It's true. Happy Lunar New Year to anybody who's celebrating. That starts today. And since I won't see you tomorrow, Ramadan Mubarak. Did I say that right? Okay, Ramadan starts tomorrow. All right. So let's play a game of name that tune, name that instrument, and if you're really good, name that artist. And I'm about to date myself. Let's see. See if we can get this to play. Everything was working 5 minutes ago.
That's the real challenge. Will it play?
Will it play? It won't play because I'm not on this. Let's try that again. Live performance. Okay, what's the song? It's the national anthem. What's the instrument? It's electric guitar. Okay. Anybody name the artist? It is Jimi Hendrix. Okay. He's actually playing to open a U2 concert. Okay. So, which was pretty interesting. All right. Got that one. Let's see. We'll just do one more here. Okay, this one takes a little bit to get going before it actually, again, another live recording. You know how concerts are. It takes them a little while sometimes to get to their piece of music. Okay. So we want song, we want instrument, we want artist, right? And if you're really good, maybe time period. Here it comes. Instruments, what are they? Drums, electric guitar, keyboard. Other than the vocal performance, every instrument here is digital. Okay? They are all electronic, from the drums to everything else. Okay? What's the song?
The song?
What's the title? It's Burning Down the House. Okay? Artist? Yeah, okay. Time period? Right, yes, okay. This is why I said I was dating myself, right? This is the song of this music of my childhood, right? My teen years, all that kind of stuff, right? Okay. Why am I playing 1980s? Okay, so I felt really bad. I felt really bad the other day because I randomly just asked, YouTube Music or something, to give me some music, and it said, would you like some classic rock? And I said, sure, and it started playing the 80s and 90s. Classic rock when I was growing up was the 50s. Right? I know, so I've got, right. Same distance, right? And then my brother-in-law, who is a DJ, came to visit, not this weekend, but last weekend. And he's been playing around with AI music to do interstitial connections, like during weddings and things like that, to connect pieces of music together. And I have to admit, the AI slop is real, but we were having a lot of fun. All right. So why am I playing music at you this morning? Those of you in 2A, do you remember when I played music to you last time?
When we were doing standing waves.
When we were doing waves, right? Okay. And you may not remember this, but I promised in Physics 2B there would come a day, because some of you said, why are you playing classical music, Mr. Balogh? Well, I was playing classical music because we were going to talk about how strings and woodwinds make their sound. Well, today we finally get to talk about how electric guitars and other digital forms of music are created. And the answer, okay, is going to actually explain everything. It's just going to explain everything. It's absolutely fantastic and magical, and maybe you'll understand here in just a second. But it all comes down to that man, Michael Faraday. He's back, okay? Michael Faraday developed an idea. It was in concept, of course, because Michael Faraday's math was more or less non-existent. But he was able to conceptualize of an idea called electromagnetic induction. That's like really big words for a pretty basic phenomenon that takes place. And I'm going to show it to you now, if I can get this thing to work. Okay. By the way, if the videos today are copyright struck by YouTube, I'm going to have to cut out that whole first section of the lab. Okay, what do I got? Over here on the Elmo, I've got a coil. It's a solenoid of wire. You really can't see the whole thing at the jeopardy of messing everything up, okay? There's that big solenoid of wire, right? It's just a bunch of windings of wire. There's like, I think like 3,000 windings in this solenoid. And this solenoid is connected to this device called a galvanometer. It's a primitive voltage sensing device. And before the days of digital multimeters and things like that, they were able to sense voltage and current by having a needle that was essentially balanced, and then when anything would happen, the needle would deflect. Okay, so it's an old-timey way of measuring voltage. Okay, so what I have in my hand right here are some magnets. Okay, they're inside a little plastic container so that I don't pinch myself and all that kind of stuff. But these are neodymium rare earth magnets. They're pretty strong. Okay, and I'm about to demonstrate for you Faraday's law of electromagnetic induction. It kind of happens quick, so just watch. What happened? Needle go boom, right? Okay. Why did needle go boom? Needle's not going anywhere right now. So what happened? What does this have? This is a magnet, so it has north-south magnetic field, right? Okay. In order for the needle to deflect, what must happen? Okay. Hold on a second. I'm holding, here, I'm going to set this magnet down inside. Okay? With the magnetic field not changing, right? Nothing is happening. The only way I can get the needle to move is to move the magnet in or out, right? If I stop, nothing happens, but if I pull it back out, something does happen, right? Okay? Right? There needs to be some sort of, like it seems to be tied to motion here. Okay? Goes one step further though. I can take this magnet and I can rotate it around. So here I'm not moving it in and out. I'm just rotating it. I could rotate it inside the coil, but then you couldn't see what I was doing. Okay? But you can see here as I rotate this thing that the thing goes back and forth. But if I just set it there, nothing happens, right? You've just witnessed Faraday's law of electromagnetic induction. So what is Faraday's law of electromagnetic induction? What does it mean to induce anything? Nowadays it means get the baby to come faster, right? So when a doctor induces a birth, right, what are they doing? Making it happen. They're causing something to happen, right? Okay, so that's the induction part, right? Electromagnetic. Magnets make electricity and vice versa, right? Electro, all this electric field stuff that we've been talking about. Voltage happened, right? Our primitive voltmeter showed that voltage was occurring, okay? It was caused not by the magnetic field, but because magnetic field was changing. What you have just seen has invented our modern society. It's a generator, okay? Because I just took a magnetic field, right? A magnet, and I move it, and I get voltage. Do you notice what kind of voltage it is? AC or DC? It's alternating, right? Okay? When we generate electricity, it's naturally alternating current. Okay? We can turn this idea around, but like stop there, right? How important is electricity? Pretty important. Like my kids, when they were little and the power would go out, they didn't know what to do. They weren't scared because we'd been camping and all, right? Okay, so it wasn't like it was, but like they literally didn't know what to do. They just kind of stood there. I'm bored, right? It's become one of the essentials, really, like water, okay? In fact, United Nations World Index uses electricity as one of the key things that determines standard of living in a country. There's some other things like access to healthcare. Okay, and then there's electricity, there's housing, there's clean water, and then there's one that always surprises me. It's one of the key metrics for standard of living. Anybody know what it is?
Transportation? Air. I'm assuming it's not food.
Glasses.
Internet access.
What? Oh.
There is a direct correlation to the access someone has to the internet and their ability to raise their standard of living, to get educated, to get advice, to telemedicine, to connect to markets, find jobs. Like it's pretty, dare I say it's necessary? I want to be very careful. TikTok is not necessary, okay? But the connection and ability to get to trade markets and education and medicine and information and all that kind of stuff. It's one of those things that is considered in the overall calculation and statistical measure of quality of life. All right, so what does all this have to do with us and what we are doing now and Michael Faraday, and why does this answer everything? Well, the first thing we have to talk about is something called magnetic flux. We actually skipped electric flux when we skipped Gauss's law back in the first unit, but that was okay. You don't really need to know Gauss's law. However, we can't get anywhere with understanding how the universe works without talking about magnetic flux. So flux. Flux is a fancy word for sort of, this is a lie, but it's a good one, flow. Okay? Flux is a measure of how much one thing passes through another. So if you have, say, a dam on a river, you can measure the flux of water through the dam, right? As the dam lets water flow, you can measure the amount of water per time or whatever. That would be a type of flux. In magnetism, and this exactly is mirrored with electric fields, right? But when it comes to magnetic fields, what we kind of do is we can do lots of things. We think of an area, and I apologize again, I'm starting to draw three-dimensional. shapes, which is going to lead us astray, right? Let's say we've got like magnetic field that's passing through. How am I doing here? It was a good weekend. Got a little bit of rest. My neck is still hurting me, but I'm getting more sleep, which I don't understand the correlation there. But all right, so we've got these field lines, right, that are sort of passing through this imaginary sheet, right? This sheet doesn't have to exist. It's just like a way to say I'm looking at this area, right, in space. The flux would be the amount of magnetic field that is passing through that sheet. And we calculate it. The symbol we use for flux is the Greek letter capital phi. We'll put a little sub b on it because it can be magnetic flux or electric flux. It doesn't really matter. And this is just b times a times the cosine of an angle. Okay? And we'll get the angle in a second. B, magnetic field, of course. A is going to be? Good guess. Area of this sheet, right? Whatever that area is. And as you now know, area is a vector. Which way would the area point in my diagram here? Perpendicular to the surface, right? And so what would the angle here be between that area and these magnetic field vectors? Try again. 0. Okay, they're both pointing in the same direction. Okay, so cosine of 0 is 1, right? So this would just be the magnetic field times A. Units here, again, we're getting kind of weird in our units. Magnetic field has units of Tesla, right? And area is? It was a good weekend, wasn't it? Yeah. Meter squared. Good job. Okay. Some prior knowledge required. Okay. This does get a new name. I would encourage you to leave it as Tesla times meter squared. But this is also referred to as a Weber. It's spelled, in the United States, we'd say Weber. Right? Okay. Yeah, that's a WB. Okay. But Weber was a German, and so that would be pronounced Weber. But we usually say it's just the units of Webers. We don't use that unit terribly often in physics. We usually just say a Tesla meter squared, right? Just to, I guess, take the German out of it. I don't know why we do that, but we just do. Okay, why am I talking about magnetic flux? This concept and idea of capturing field passing through an area is vital to understanding Faraday's law of electromagnetic induction. When I had this coil over here, it's going to be a miracle if we get through this lecture without any technical glitches, okay? When I had this coil right here, right? Okay? Does this coil have an area? Yeah. What would you? How would you calculate it?
Area of a circle.
Area of a circle? Oh, geez. What's the area of a circle? Pi r. It's either 2 pi I or pi r squared, and you have a 50-50 chance, right? You don't, because r squared is the giveaway, right? Area has to be in meters squared, right? So it's not 2 pi r, because that doesn't have the right units, right? Okay, so pi r squared would be the area of that coil right there, right? And then I have magnetic field, don't I? Right? So if I come and I bring this into the area, the needle deflects. But if I leave it inside of there, is there magnetic flux? Is magnetic field passing through the area of the coil? Yes. But there's no Faraday's law of electromagnetic induction, right? There's no voltage being created. So what is necessary, therefore, in order for voltage to be created? There has to be movement, and more precisely, there needs to be a change of something. Okay? We'll get to that in a second. Okay? So we're going to write it like this. This is curly E, okay? That was a human mistake. That wasn't a technological one. The technology is not yet at the point where I can just have it read my mind and switch over. All right. So this curly E right here is, did we encounter this symbol before?
Is that epsilon?
It's not energy. This is voltage. I'm sorry. I'm not responsible for this, okay? This is the symbol for EMF, which I know we have talked about before, okay, electromagnetic force, okay? But it's in units of volts. So E is often used as a symbol to talk about the change in voltage of something, okay? You can just interchange V, capital V and curly E there. I think the actual symbol is supposed to be like something like that. It's an E with an Elvis hairdo. I don't know what it is, okay? But that's what it is. It's just voltage, right? So Faraday's law of electromagnetic induction is going to give us the voltage. When, okay, I'm gonna write the whole thing, I'm put it in a box, and then we're gonna tear it apart, okay? Don't panic. Well, actually, when you learn about that minus sign, you are gonna panic. What's capital N? It's just a number of turns, right? So for a single coil, which I don't have over there, a single coil will be N of 1. But since that one has 2,500 turns, I would put 2,500 in the front of my calculation. The real deal, the real meat here, okay, comes from a change in magnetic flux in time. This is the way your book writes it. In your book's not wrong. Your book is absolutely correct and true. I personally don't like the minus sign on the front. The minus sign is there to remind us of something called Lenz's law, which we'll talk about later, and it is really going to melt your brain. Mr. Balogh will often write this one like this. What's the difference? Absolute value sign, right? Okay, because when you calculate the voltage, you really just need, because voltage is a scalar, right? It can be positive or negative, but you don't really care about the direction that the voltage is going because it doesn't make any sense, right? However, the negative sign in Faraday's law is telling us something very important. Voltage is produced in a way that fights against the change in flux. Do you see the change in flux in there? It's a delta flux divided by delta time. So that delta means change, right? It means final minus initial for all of those things. So if the final and the initial are the same, there's no change, and so therefore there's no voltage and there's no electromagnetic induction. So we need that change, and that's really what we're going to spend our day today really talking about are these changes in flux, because this is kind of a difficult thing to wrap your brain around. We might get to the minus sign. We'll see how far we get, okay? So either way of writing it is just fine, whether you use the absolute value signs as a reminder that, okay, this could go either way, or you put a minus sign in, okay? It doesn't really matter. The minus sign and the absolute value signs are both telling us that there's an opposition here, a fight that's going on. But we'll get to the fight later. Okay? So just take, what are the units of E? Volts. I know it's a Tesla meter squared per second or a Weber per second. Just go with it. Just okay, stay in standard units and you'll be fine. Okay? So don't try to break down the units or try to figure out anything that's going on there. Okay, so how do we change the flux, right? That's really the question, right? What are all the ways that we can change the flux? So on the last slide, right, we learned sort of a mathematical description and a little bit of a conceptual idea for what flux is, right? It's this way of counting a field passing through an imaginary area. Like the area of that coil is very real, but it depends on the size of the coil. Like we can't see the area, we can calculate it. All right, so if we take a look at all the ways that flux can change. So we know that flux, right, is B times area times the cosine of the angle between them. And so when we come in here and we say delta, right, we are deltaing something inside of those parentheses. What you do to one side, you do to the other. So what are all of the possible ways you can change the magnetic flux? Look at the right-hand side. What can the delta affect?
Area, the field, and the angle.
Okay, so there's basically three things over there, right? We can have a delta B, or we could have a delta A, or we can have a delta angle, right? Okay. Now, could all three be happening at the same time? Sure, that's called graduate school, okay? We're going to try to make sure that really only one of them is happening at a time, okay? But what would a change in magnetic field look like? Like, with my example over here with the Elmo, right? What was I changing the area of the loop? No. Okay. I was making this magnet be closer or further from the coil, right? So I was changing magnetic field. Magnetic field has a strength that is like 1 over R, like for wires and things. I know this is a permanent magnet, so it's not quite the same. But the idea here is, right, that I can change the distance, right, that this magnetic field is from this coil. So right now, there is magnetic field through the coil. Even if I take this magnet way over here, there's magnetic field through that coil. Why? Because Earth has a magnetic field, right? Okay. Now, is the Earth's magnetic field changing? No. On a 1,000-year time scale, sure, but like not right now, right? Okay. So there's magnetic field, but it's not changing. The delta B is 0 right now. The delta A, the change in area of the loop, is 0, right? And there's no angle happening, right? So as I bring my magnet closer and closer and closer, and I increase the magnetic field strength in the coil, the needle deflects, right? But then I stop. So is the magnetic field changing right now? No, it's the same before and after for any moment of time. And then if I take it out, the magnetic field is decreasing now. I'm moving the magnet further and further away. And so I again have that change. So was the magnetic field flux increasing or decreasing as I bring the magnet towards? Why do you say increasing?
50-50 chance.
Okay, good, right? Guessing's just fine, right? Okay. But why would it be increasing if the magnet's getting closer? Remember, a delta is a final minus an initial. Yeah. The final here is going to be bigger. The magnet's closer at the end, right? And the initial was small. So take big minus small, big number, right? Okay, so it increased. Okay. So now if I take this magnet and I pull it out, I know. You guys are sitting here going, Mr. Bailey, you're just pulling magnets in and out of a coil. This is the dumbest thing in the world. Right? All of your life depends on this. Not like immediately physically, but like all of your life. Okay. So now I come in here and I pull this out, okay? And I pull it out. Is the flux getting bigger or smaller? Smaller. Why? It started out big and it ends at 0, right? Far away. And that's a negative change, right? So we say the flux decreased. Okay? But it all changed because the magnetic field strength changed. The area stayed the same and the angle stayed the same. Let's skip over area for just a second. How would I change the angle but keep the magnetic field strength the same? Okay, this is where, remember the area vector. Where's the area vector for this coil? The area is the circle right here, right? All this area. But where's the area vector? Area vectors are always perpendicular to the area itself, right? So it's either sticking in or out. Let's just say it sticks out directly at you out of the screen, okay? So if I come and I take my magnet and I put it right there, right? And I turn it. It's hard for me to twist it around in 360 degrees, right? So I'll just wiggle it back and forth, right? I'm not changing the distance that the magnetic field is from the coil. All I'm doing is changing the angle between the magnetic field and the area vector of this coil. So rotate something, right? Either rotate your magnet, in other words, change the orientation of the north and south that the magnet's giving off, or rotate your coil. A little bit harder for me to do in this demonstration, but the net result is the same, right? We're changing the orientation of the field with respect to the area of the coil, and that gives rise to a voltage. All right. How would you change the area?
Compress or
We'd have to physically alter the size of the coil. Now, in terms of engineering and mechanics, that's actually really hard to do. There's one example I'll give later that we'll be able to do it fairly easily. But in general, a generator isn't changing the area of the coil in it as it runs, okay? What can you guess, or do you think that a generator is actually doing?
so either twisting the magnet.
It's rotating something, okay, because it's an engine and it just sits there and rotates. So it's either spinning a magnet inside of a coil, or it's spinning a coil near a magnet. It actually does both. But like, it's not changing the physical size of the generator, right? Okay. So changing the area's magnitude is not a physically important idea, okay? We usually are going to change the strength of the magnetic field B, or we're going to change the angle, the orientation that that magnetic field makes with the area. We try in this at Physics 2B to just change one of those at a time. Can we change area? Yes. There'll be just a couple of specific examples, and those are really the only examples you need to worry about when it comes to area. Okay, movie time. Just again, I'm trying to give you visualizations, something for your brain to latch onto as a picture for what's going on here. And please work.
Magnetic fields apply forces to electric charges, but only if the charges are in motion. The direction of the force is perpendicular to the velocity and the field, and depends on the sign of the charge, in this case, negative.
This is the Lorentz force law. We did this before, last chapter.
For example, the charges might be electrons in a piece of wire. Just moving a wire through a magnetic field makes a current try to flow. But the field of a bar magnet can be perpendicular at every point to a circular loop of wire. So, moving the loop creates a force that drives a current all the way around the loop. The current flows one way if the loop moves upward.
Changing the flux, causing current and voltage.
The other way if the loop moves downward. Of course, a current also flows if the loop stands still and the magnet moves.
So it doesn't matter which one's doing the moving, right?
Moves downward. The other if the magnet moves upward. In fact, Faraday found that any method of changing the magnetic field through a circuit would make a current flow.
I wanted you to see, right, that it doesn't matter like who's doing the moving or what's doing the moving. It's just you need a change, right? Something needs to be changing. And the video also kind of alludes to the fact that Faraday's law of electromagnetic induction is the result of the Lorentz force law, which we did last chapter. We're building on that idea, even though your textbook doesn't like directly connect those things, okay? All right, back to the beginning. I played you some music where electric guitars featured prominently, right, at the beginning of class. Any guitar players out there willing to admit it? Electric or acoustic? Electric, okay. Can I ask you a couple questions? Have you ever had to replace a string on your guitar? No, okay. An acoustic guitar, the answer would probably have been yes, okay. But an electric guitar, the answer is usually no. That's because electric guitar strings are different, okay. Acoustic guitar strings are made out of metals and some plastics, resins. Electric guitar strings are made solely out of metals, okay, and actually contain little tiny bits of magnet in them, okay. So you can't see it, right, but there'll be like little bit of magnet, little bit of magnet, little bit of magnet. There's magnetization built into these strings, okay. All right. In order to make your electric guitar work, what do you need to do? You got to plug it in. Okay, right? And you plug it into what? An amp. Okay. So there's an amplifier. If you don't plug your guitar in, have you ever played it with not plugged in? Does it make noise? It doesn't? Little tiny, tiny bit, doesn't it? Okay, so two things here. The department would not buy me an electric guitar. Okay? They said, you're going to have to just buy your own electric guitar. It's like, no, it's for demonstrations, right? Okay? Number two, I can't play guitar, right? So it wouldn't help anyway, right? But plugging in the guitar seems obvious, right? Like it's an electric guitar, right? So it needs actually doesn't need electricity to make noise. It can make noise from the vibrating string just like any acoustic guitar. The difference is that electricity is used to amplify the sound. In an acoustic guitar, the body of the instrument, that hole and the size of the wood cabinet and everything it's attached to, that's used to amplify the sound, to make the little tiny vibrations on the string much bigger. In an electric guitar, the amplification is carried about through these things called pickups. And there's a row of pickups right here. Can you see those? Okay. And then they're out of focus, but there's another row of pickups right there. What do you think a pickup does? It's what it says on the tin, right? It picks up the vibration of the string. How? By Faraday's law of electromagnetic induction. Here's the side of a pickup. So I'm like drawing you sort of a cutaway view. So like the pickup, is in a metal shell, but inside that metal shell is a coil of wire. The string is going across the top, and remember, there's little tiny magnets in this string, okay? As the string is set into motion, as it's strummed or plucked on the instrument, the string begins to vibrate. It begins to oscillate with all of those beautiful standing waves you learned about in Physics 2A. And oh my gosh, I can't believe you said that, Mr. Balogh, because you're causing me PTSD from Physics 2A. It's okay, right? So we got this wiggling string, right? Okay. The strings have magnets in them. What are these magnets doing? Wiggling near a coil. Faraday's law of electromagnetic induction says that if we change the magnetic flux through a coil, we will generate a voltage. And since Ohm's law exists, any voltage with any resistance means there's going to be current there too. So a voltage and a current are generated in the pickup, right? Just like my coil over here, I was moving the magnet, right? Whatever frequency I moved that magnet at, however fast I rotated it or slow I rotated it, would be exactly the same frequency as the voltage oscillation in that coil. So in an electric guitar, you set the string into vibration. The pickup, via Faraday's law of electromagnetic induction, gets exactly the same frequency as the vibrating string. That oscillation, this is not to scale, is then sent to an amplifier, okay, where that small, tiny voltage and current gets magnified and then attached to a speaker, right, where you can then melt your eardrums if you want to. Okay? What does Faraday's law of electromagnetic induction sound like? Sounds like an electric guitar. Because you can't get an electric guitar without Faraday's law of electromagnetic induction. It's simply impossible. Electric guitars sound very different. I played two pieces of music. The style that Jimi Hendrix sort of pioneered involved a lot of distortion and also some physical changes to the tension of the strings on the guitar. Was that called the whammy bar? That allows you to change the tension on the fly. And then there was sort of the digital music of the 80s, 90s, and current, right, where a lot of things are synthesized. You can make an electric guitar actually sound like anything, because once you have this oscillating voltage signal, you can connect it to the amp, and this isn't correct, but you can put in line with this thing, you can put this thing called a DSP, a digital signal processor. Okay? The DSP takes that oscillation and then turns it into digital ones and zeros, which then can be output pretty much as any synthesized waveform. My brother-in-law is a musician. He plays electric guitar and steel pedal guitar and acoustic. He plays guitar. He has well, it's actually kind of fancy now because he's made money finally. But he used to have it in a suitcase. And he would flip open the suitcase and there'd be a series of pedals in that suitcase. And while he was performing, he could push a pedal and change the sound of his guitar, right? So if he wanted to play something in the Hendrix style, he could push up a pedal, right? But if then he wanted something that was a little less raucous, he could push a pedal and get a more classical sounding guitar, whatever, right? So he and I were geeking out over the electronics and things like that, and he very much believes that vacuum tubes are better than solid state, and we can have that fight later. I love my brother-in-law, but he's wrong. And he left the room. That was a mistake. Because the thing with a digital signal processor is you can load any waveform into it. And so I programmed all the pedals to make animal noises. Right? Chicken, elephant, whatever, right? Okay? Because they're just MIDI files you download from the internet, right? So I threw it on there. He came back, he started practicing, and it was chicken, right, coming out. And then it was elephant, and then it was giraffe. And then he's like, looked at me, and I just left. Yes, very fun. So basically, all of modern music, from drum machines to electric guitars to electric pianos, like you can just ask me about any instrument, I can tell you exactly how it's going to work because of Faraday's law of electromagnetic induction.
Is there an electric flute?
I think there is. I know there's electric like violas and violins and things like that. Woodwinds, you don't actually blow on them. The electric versions, you're just pushing keys. Because I know there's like electric clarinets, which I was always like, I was a clarinet player in middle school, and I was like, why? I mean, it's a woodwind. It's like in the title. Anyway.
Mr. Halo,
What?
as the electric guitar string moves, is that a change in the angle?
It's a change in magnetic field strength. It's actually several changes, right? This would be kind of graduate school level stuff, right? But okay, so but yes, it's changing for us. I'd say changing magnetic field strength. We're changing the distance like away from the magnet as it goes back and forth. Okay, so what else can we do with Faraday's law of electromagnetic induction? I said it's going to explain everything. I wasn't kidding. Oh, that was the picture of the pickup. What's this?
It's my microphone.
Point to the closest microphone.
Our phone. Your phone. Yeah.
Okay?
Any speaker on the microphone.
Okay, right? Okay. They are everywhere. Facebook is listening, right? They are everywhere, these microphones, okay? Didn't used to be, right? But they're everywhere now. How does a microphone work?
Vibrations on a sheet of.
Okay, so there is, I don't have a picture. Oh, do I have a picture? Yeah, I do have a picture. Look at that. I prepared. Jeez, it happens, right? So somebody is talking into a microphone. Sound waves come in, strike a diaphragm. This is a piece of rubber, plastic, or something like that. And that diaphragm begins to oscillate, okay? And as it oscillates, that diaphragm has a magnet on it or is attached to a magnet, which starts oscillating that magnet. And if you put a coil of wire near where that magnet is bouncing up and down, what are you going to now have in the coil of wire? An electrical signal that exactly matches the frequencies of the sound that hit the diaphragm in the first place. By the way, reverse this process and you have a speaker. Use electricity to wiggle a magnet connected to a diaphragm and it produces sound, right? So on either end of this, okay, Faraday's law of electromagnetic induction is doing the work, right?
Basically anything could be.
Yeah, more or less, but there are pleasant ways to make sound and there are not pleasant ways to make sound. And I am not talking about the actual music itself. I'm talking about the quality of the waveform that our brain interprets. So, but that's a different discussion in the realms of psychology, and I'm not an expert. So, electric guitars, brought to you by Faraday's law of electromagnetic induction. Speakers, brought to you by Faraday's law of electromagnetic induction. Microphones, brought to you by Faraday's law of electromagnetic inductions. Few things about microphones. Yes, that is how you sound to other people. Anybody that's ever stepped up to a microphone and spoken into the microphone has had that existential angst of, wait, do I sound like that? The answer is yes. That's how you sound to other people. Why do you sound different in your head? I mean, obviously, this is James Earl Jones. That's what I hear when I speak.
Because your bones.
You're hearing a lot of your voice as vibrations through your skull. Okay, it's coming up from your larynx, and it passes through the bones of your face into sort of a back channel, not outside. You get a little bit of the echo, like the sound leaves your voice, bounces off the walls, comes back to your ears. Your brain largely ignores that signal. It goes with the signal that's mostly coming up through here. Because if it did try to, bring the two together, they'd be out of phase and it'd be nasty. So we've evolved to sort of hear the voice in our head. Okay? And when you step up to a microphone, you will sound different. I'm used to it. I've done so much recording of myself and public speaking and using microphones that I don't think about it anymore. I know that my voice is kind of high-pitched and squeaky and not pleasant to listen to, but you guys come anyway. It's kind of amazing. Well, it's not James Earl Jones. I know that, right? Okay. All right. Let's. Do I want to do that calculation? Yeah, let's do it. Let's do it. Let's take a little break from the concept here and the application, and let's just do a calculation. Let's show you how to run with a calculation of Faraday's law of electromagnetic induction. I want to say this right now. This is not going to be the hard part. Okay? The concept's going to be the hard part for stuff that's coming up. We haven't talked about the minus sign yet, right? Okay? But if we are going to find an EMF, right? If you're looking for a voltage, we're either doing last unit, where there's like a charge and we want to find the voltage of it, right? Or we're doing a circuit and we need to find the voltage in series or in parallel. But here we're going to be finding a voltage, and like the dead giveaway is the word induced, isn't it? We're creating a voltage from something, right? So again, context, right? Reading the problem. It's easy on homework to say, well, this comes from chapter 22, so therefore I know it's Faraday's law of electromagnetic induction. But when you're on an exam or later, right, and like, how do you know? What voltage are we talking about here? Well, the answer is it depends on the context. So we know this has to be Faraday's law of electromagnetic induction, so we might as well just start there, right? Like, we know the EMF. I'll go with what your book does, but realize that I'm going to kind of ignore that minus sign for right now, okay? All right, so we need to sort some stuff out. Are we given anything? We're strategizing here, right? So like, is there an N? Like, what's the change in flux? Like, so change in flux, that can be a delta of either B, A, or an angle. Maybe we should visualize first. That's probably the first step that we should probably do, right? What's a lightning bolt look like? Okay, there's a lightning bolt. There was lightning last night.
Yeah, that was awesome.
Okay, so there's the cloud, there's the ground, okay? And then we have a coil of wire, several like turns, right? Okay, matter of fact, how many turns?
100.
100 turns, that's the N, isn't it? Okay, and we know the radius of this thing. It's 0.8 meters. Okay, so I got that. And then, the distance. And they told me to treat the lightning strike as what? A straight wire. So that just kind of makes it a little bit easier. Okay, and we know that the distance there, right, is 200 meters. So again, just kind of visualizing, get an idea of what's going on here, right? Okay, to find the EMF, I'm looking for this. What do I need to know? I need to know N. Do I know N? Check. Okay. I need to know change in flux. Do I know change in flux? Not yet. Do I know change in time?
Yes.
Yeah, okay. So 10.5 microseconds is 10.5 times 10 to the minus 6 seconds, right? So this is my delta T. I have my delta T, I have my N. Now I just need to unpack this change in flux, right? So what's changing here? Can we go through and like figure out like where is the delta being applied, right? What's the change? Is the area of the coil changing? No, like the physical size of the coil is not changing. So that means that I can pull that out. It's at least one of the things I can pull out of the delta because it's constant. It's not changing. It's just going to go on. It's just going to be there for the ride. Okay. Is the coil rotating? So what else isn't changing? The angle. Okay. And in fact, we're going to let that angle be 0 or 180 just to maximize this. Okay. I did draw this correctly to maximize it. This is a good warm-up for what's going to happen next. Okay. Let's do the right-hand rule for the lightning bolt. Let's see if I aligned my coil correctly, right? To get maximum flux, I need my area vector and my magnetic field direction to line up, right? Okay. So, right-hand rule. How would I apply the right-hand rule to the lightning bolt to find the direction of magnetic field? We have two choices of right-hand rules from last chapter, right? We got a handshake and we've got a hitchhiker, right? Which one are we going to use? Handshake or hitchhiker? Why?
Because it's a
Because we're only looking for field direction. We're not worried about, there's no force being mentioned here at all, right? So no force involved, therefore it's got to be the hitchhiker. We're looking for magnetic field direction. Now it comes down to a choice. Is my thumb the current or are my fingers the current? Thumb. Why thumb? Because the wire is straight. So now we have to argue. Does lightning strike up or down?
depends.
The answer is yes. Okay. And sometimes it just meets in the middle. Okay. Right? So it all depends on how good your eyes are at integrating information rapidly or what the shutter of the camera is doing. But the answer is yes. Okay. So let's go up. I don't care. Up or down. Actually, it doesn't matter. Right? So if I point my thumb up, over in where the coil is, which way is the magnetic field pointing? Into the screen, right? If the lightning struck down, which way would it be pointed? Out of the screen. Either way, it's in or out of the screen, right? And which way did I draw my coil? Which way is the area of that coil pointing? In or out. So I made sure that they lined up in my picture.
Nice.
Right? So the angle here is also not changing. Okay? So we'll do cosine of theta, but this whole thing is going to go to 1. I'm going to make sure that my theta is equal to 0 or 180 or whatever, right? This is where it doesn't matter that minus sign is actually on that equation, right? Because I can flip-flop my areas however I want. Okay? And then that just leaves delta B, doesn't it? It's the only other thing that can be changing. How is the magnetic field strength changing? First of all, is this wire or lightning bolt going to make a magnetic field?
Yeah.
Yes, right? So what changed?
Well, the lightning. Here.
It appeared, right? There was no lightning bolt, and then there was a lightning bolt, right? Okay. It took 10.5 microseconds for it to happen, but there was no magnetic field, and then all of a sudden there was magnetic field, right? So our change, like our initial is 0, but our final is whatever the magnetic field of a lightning bolt happens to be. Well, I don't know the magnetic field of a lightning bolt, but I do know the magnetic field of a wire. I know this is going to be a B final minus a B initial. I know that my B initial is 0, no lightning, right? So the question is, what's the magnetic field of a lightning bolt? What are the hints in the problem? It's a straight wire, right? What's the magnetic field of a straight wire?
M naught I over 2 pi.
Mu naught. Mu naught I over 2 pi r. That is not circumference, by the way, in the bottom. It just happens to be 2 pi r. Where that r, this r right here is the distance from the wire, right? Okay, not to be confused with the other radius that we need for area, right? Okay, now we have to put this all back together, right? Okay, what is my change in magnetic flux? It's a change in magnetic field times area and cosine of 0, which is 1, right? So what is that going to be? That's going to be, my delta B is just mu naught I over 2 pi. I'm going to put D for distance just to make sure I don't start confusing R's in my math. Okay? Times the area of what?
Of the coil.
Pi radius of coil squared. So there's my change in flux. I can get a number by plugging in numbers for this one. I got my change in flux to be 6.03 times 10 to the minus 3 Webers. No, that's a lie. This number right here is my change in magnetic field. Teslas. it's this number right here. That's that number. And then I'd have to multiply it by pi r squared in order to get the flux, which I did not calculate, because what I did is I took this, and I said, look, my EMF is going to be N. I'm going to drop the minus sign because I don't care. 100, okay? I know that drives you guys nuts, right? Times my change in flux, which is 6.03 times 10 to the minus 3 times pi times 0.8 squared, all over 2 pi times 200 not squared, divided by 10.5 times 10 to the minus 6. Did we get it all?
Yep.
We got a mu. Oh, no, I calculated that. Shoot. I went too far. I got too excited. There we go. That's what it is. Okay? Put too many things in. This is why I don't like doing numbers first. All right. So that should do that. And that will give me an EMF of 116,000 volts, which is kind of small for lightning standards. It's not the voltage in the lightning bolt. It's the voltage induced in the coil 200 meters away from a lightning bolt, right? So power lines that you'll see like over by 99, those are 500,000 volt lines. Actually, there's a line on there that goes 750,000 volts, but don't worry about that. 500,000 volt lines. We have megawatt lines running up and down the state. Megavolt lines over there by like Highway 5, the megavolt return line. The stuff you see like in a neighborhood or something is usually 25,000 volts. So this is sitting somewhere in the middle. So question, why aren't we collecting electricity from lightning bolts?
How do you know where they're going to be?
Slow.
Too slow? 10.5 microseconds?
How do you know where it's going to be? Well, you can make it straight.
Well, I know exactly where it's going to be.
Don't we do that? What?
The answer is Florida.
Well, don't we do that in tall buildings? We
Their
have things
fault
that-
or their help?
No, they're
we
in
just not collect?
they're in Lightning Alley. What?
Don't we have like rods on the top of like tall buildings?
Yeah, that's just to keep the building from getting hurt by a lightning strike. Okay? Lightning strikes the surface of planet Earth 100 times per second. What's the problem?
Most of them, how are you going to?
Earth's a big place. Actually, most of it's over the ocean. Okay, right? So it's hard to get to. It's not consistent. A power grid needs the ability to provide power constantly, not just every once in a while. The time between lightning bolts in Fresno is what, months? What's that?
Too slow.
Too slow, right? Okay. So the energy's there, of course, but it's a very not feasible way of doing it. Okay. Back to how Faraday's law of electromagnetic induction is your everything. What's this? This is a hard drive. This is a very hard drive, right? Okay. This thing, okay, came out of a server rack. Okay, from the early 80s. Okay, did you sense a theme today? Back to the Future. By the way, the flux capacitor in Back to the Future. What's a capacitor? What does a capacitor do? Stores stuff, right? Stores charge, stores field, right? What's flux? That passes through something else, right? So the flux capacitor is an oxymoron. It's an inside joke that the writers coined. And the flux capacitor made time travel possible. Yeah, when you know science, movies can be pretty fun. And it was done on purpose by Robert Zemeckis. Okay, so this is a hard drive. This hard drive, I believe, I'm pretty sure I'm right on this, stored 1 megabyte. Okay? what is that, 1/250 millionth of a song or something like that for today, right? 250,000th of a song. I might be off by a few zeros. But the point is, right, that in your pocket, you're probably carrying a minimum of 64, probably more like 128 or 256 gigabytes of information, okay? This thing stored 1,000 times more information than the computers did that took us to the moon during the Apollo program, right? Okay. But this is 1 meg. You imagine carrying this around in your pocket, right? Only to be able to read like one Excel document, right? Okay. Right. Okay. So why am I talking about hard drives? Hard drives are brought to you by Faraday's law of electromagnetic induction. There's a spinning disk in here, isn't there? Okay. That spinning disk has little pieces of magnet on it. As a matter of fact, the surface of these disks have areas that can be magnetized by the read-write head, which is down here. This moves in and out, and the disk spins underneath that read-write head. Okay. So, decided to catch up. Okay. So the read-write head, okay, has a coil in it. It's got several coils actually, right? And as it spins, as this head floats, it floats really close to the surface of the drive, okay? And as these disks spin around, you're getting magnets moving underneath these coils. As the magnet moves underneath, there's a change in magnetic flux. The coil senses that there's been a change in magnetic flux, and so therefore there's a voltage, and it sends that voltage signal onto the drive's controller. The drive controller goes, oh, signal. That's a 1. And when it doesn't get a signal, that's a 0. You can reverse that process. You can record information to the surface by altering the magnetization of the surface through the write head. The write head makes magnetic field to cause the surface to change. The read head simply reads the magnetization of the surface. Make that happen really, really fast, and you have the ability to store information permanently. Hard drives are not old-fashioned technology. This one is, okay? But hard drives form the backbone of everything we do on the internet nowadays. That cloud of stuff that's out there, right? Okay? It lives on the backbone of hard drives, and believe it or not, tape is still used to back up information, because tape drives are actually really good at holding on to information. They're just not very fast. So if you want to archive something in a server farm, you can put it to tape. If you need something that can be accessed fairly quickly, you want it on hard drives. And then things that are accessed all the time, like TikTok, like the most popular video on TikTok or whatever's going on, those are put onto parts of the server farm that contain solid state devices, because those are really fast. They're very expensive, but they're very fast to get the information in and out. For stuff that you don't need as immediately, hard drives are a nice cheap solution for lots of storage. And then you can do the tape backups. Tape backups are kind of going out of style, but they're still being installed in new server applications. So the information storage infrastructure of all computing after the 1970s, brought to you by Faraday's law of electromagnetic induction. Every motor, every generator, every microwave oven, every wireless internet signal, as we're going to discover, is brought to you by Faraday's law of electromagnetic induction. I'm going to get these dates wrong, but I'm going to be close. I'm going to be within a decade. In 1880-something, an Italian physicist pulled off what everybody thought was impossible. His name was Edward Marconi. Marconi sent a signal from one side of the English Channel to the other. I think he was in France, which was a mistake, and he was sending a signal to Great Britain. That was the world's first wireless transmission of information over a distance of more than just a few feet. Okay? Well, no, it was a proof of concept. Okay? Marconi was able to pull that feed off because of Michael Faraday's work and Faraday's law of electromagnetic induction. I know you don't see the connection right now, so you just kind of have to trust me. But this is where we are going. We're going to explain every radio signal, every Wi-Fi signal. Anytime electricity is generated at PG&E, at a dam or a gas-fired power, this doesn't work for the sun, that's quantum mechanics, that's something else, right? But like, I'm hard-pressed to find an example where Faraday's law isn't being used, right? Okay? I could probably count on one hand, right? Everywhere else, Faraday's law of electromagnetic induction is being used, okay? And it is one of those fundamental aspects of our modern world. I'm going to stop there because we don't have time to do the quiz. So guess when the quiz is going to happen? Thursday, right as we start, okay? So gave you fair warning, right? We'll start with a quiz, and then we're going to dive into that negative sign. It's going to be it's going to be rough. You're going to want to be here for that because there's a lot of right-hand rules that don't come across on the video recording. See you Thursday.